The necessity of using spaces for branch panel feeders installed underground hinges on several elements, including the type of cable in use, the depth at which it is buried, and the precise code mandates relevant to the project. The National Electrical Code, specifically Article 300.20b, generally stipulates the utilization of spaces to uphold a minimum separation among insulated conductors when these are situated inside a raceway or cable tray. This is done to avert arcing or short circuits. However, it is important to note that the National Electrical Code does not directly tackle the question of spaces for branch panel feeders that are installed underground. Within the electrical sector, it is generally seen as good practice to incorporate spaces for branch panel feeders that are situated underground, even in situations where the National Electrical Code does not explicitly call for it. Spaces bring about a number of advantages. Firstly, maintaining conductor clearance. Spaces guarantee that there is a consistent separation between the insulated conductors, stopping them from making contact with each other or rubbing. Such contact or rubbing has the potential to harm the insulation, thereby escalating the chances of fire or explosion. Secondly, reducing ground faults. Spaces play a part in avoiding ground faults by physically separating the conductors from the ground. Thirdly, facilitating troubleshooting. The presence of spaces makes it simpler to pinpoint and fix any cable issues that may surface, as they introduce a buffer zone that assists in both testing and accessing the conductors. When it comes to underground burial considerations for branch panel feeders, one needs to consider several aspects. Firstly, burial depth. The chances of the cable being disrupted or damaged are reduced when it is buried deeper. If a cable is buried at a depth of 24 inches or greater, it might be justifiable to not include spacers. Secondly, cable type. Certain categories of underground cables, like direct buried cable, are uniquely engineered for installations without spacers because they are robustly built and have an inherent separation distance. Thirdly, soil conditions. The kind of soil where the cable is laid can also have an impact on whether or not spacers are necessary. In settings with rocky or unstable soil, spacers might be vital to prevent damage to the cable. If an inspector mandates the use of spacers or insists on having a letter from an engineer, the engineer's responsibility would be to assess the variables that have been detailed and come to a determination that is shaped by their expert judgment and experience. The engineer should clearly explain in the letter the reasons why spacers are deemed unnecessary for that particular installation. To summarize, although the National Electrical Code does not specifically stipulate that spacers must be used for branch panel feeders in underground installations, it is viewed as a sound industry practice to employ them. This is to ensure that the installation is both safe and reliable. When an inspector calls for spacers or wants a letter from the engineer, it is up to the engineer to carefully weigh the considerations that have been presented. The final decision should be based on the specifics of the project and the attributes of the site. An engineer must understand the role of spacers in underground electrical installations. The primary function of spacers is to maintain a physical separation between conductors. This separation is crucial for preventing several potential problems. Firstly, electrical shorts. Without adequate spacing, conductors can come into contact with each other due to movement, settling, or external pressure. This contact can lead to a short circuit, which can cause a power outage, damage equipment, and create a fire hazard. Secondly, ground faults. Spacers help to ensure that conductors do not come into contact with the ground. A ground fault occurs when a conductor's insulation fails and the conductor comes into contact with a grounded surface. This can also lead to a power outage and create a shock hazard. Thirdly, insulation damage. Continuous contact between conductors can cause the insulation to wear down over time. This is especially true in environments with vibration or temperature fluctuations. Damaged insulation increases the risk of shorts and ground faults. Fourthly, heat buildup. When conductors are bundled tightly together without adequate spacing, heat can build up. This heat can degrade the insulation and reduce the current carrying capacity of the conductors. Spacers promote air circulation, which helps to dissipate heat and maintain the conductor's operating temperature within safe limits. There are several types of spacers available for underground electrical installations. The choice of spacer depends on the size and number of conductors, the burial depth, and the soil conditions. Firstly, plastic spacers. These are typically used for smaller conductors and are relatively inexpensive. They are resistant to moisture and chemicals, making them suitable for underground use. Secondly, concrete spacers. These are more robust than plastic spacers and are used for larger conductors or in areas with heavy loads. They provide excellent physical protection for the conductors. Thirdly, treated wood spacers. These are a traditional option and are still used in some areas. The wood is treated to resist decay and insect damage. Fourthly, manufactured duct banks. These are prefabricated structures that provide channels for multiple conductors. They are typically made of concrete or plastic and offer excellent protection and spacing for the conductors. The National Electrical Code provides guidelines for the installation of underground electrical systems. While the National Electrical Code does not explicitly require spacers in all situations, it does emphasize the importance of maintaining adequate separation between conductors. Section 300.5 covers the requirements for underground installations. This section specifies minimum burial depths for different types of wiring methods and voltage levels. It also addresses the need for protection against physical damage. Section 310.15b3 covers the dirting of conductors in raceways and cables. When conductors are installed in close proximity to each other, their opacity must be dirted to account for the heat buildup. Spacers can help to reduce the amount of dirting required by improving air circulation. Section 314.27 addresses the support of conductors in outlet boxes. While this section does not directly apply to underground installations, it does highlight the importance of supporting conductors to prevent strain on connections. In addition to the National Electrical Code requirements, local codes and regulations may also apply. It is important to check with the local electrical inspector to determine if there are any specific requirements for spacers in underground installations. The decision to use spacers in an underground electrical installation should be based on a thorough assessment of the specific conditions. Firstly, conductor size and type. Larger conductors generate more heat and may require more spacing. The type of insulation also affects the heat dissipation characteristics. Secondly, burial depth. Shallower burial depths increase the risk of physical damage and may require more robust protection, including spacers. Thirdly, soil conditions. Rocky or corrosive soils can damage conductors and may require additional protection. Fourthly, environmental factors. Areas with high moisture levels or temperature fluctuations may require spacers made of corrosion-resistant materials. Fifthly, load requirements. High current loads generate more heat and may require more spacing to prevent overheating. If there is uncertainty about whether or not to use spacers, it is always best to consult with a qualified electrical engineer. An engineer can perform a detailed analysis of the system and provide recommendations based on sound engineering principles. The engineer's letter should include, firstly, a description of the installation. This should include the location of the underground run, the type and size of conductors, the burial depth, and the soil conditions. Secondly, an analysis of the factors affecting the need for spacers. This should include a discussion of the heat generation characteristics of the conductors, the potential for physical damage, and the environmental conditions. Thirdly, a justification for not using spacers. This should explain why the engineer believes that spacers are not necessary to ensure the safety and reliability of the installation. Fourthly, a statement of compliance with applicable codes and standards. This should confirm that the installation meets all applicable requirements of the National Electrical Code and local codes. In conclusion, the use of spacers in underground electrical installations is a complex issue that depends on a variety of factors. While the National Electrical Code does not explicitly require spacers in all situations, it is generally good practice to use them to maintain adequate separation between conductors and prevent potential problems. If there is any doubt about whether or not to use spacers, it is best to consult with a qualified electrical engineer. Proper planning and installation are essential for ensuring the safety and reliability of underground electrical systems. Understanding the nuances of electrical codes and the specific requirements for underground installations is important for the following reasons. Firstly, safety. Electrical installations must be safe for both people and property. Improperly installed electrical systems can create fire hazards, shock hazards, and other dangerous conditions. Secondly, compliance. Electrical installations must comply with all applicable codes and regulations. Failure to comply can result in fines, delays, and other penalties. Thirdly, reliability. Electrical systems must be reliable and able to provide power when needed. Improperly installed systems can be prone to failures, which can disrupt operations and cause inconvenience. Fourthly, cost effectiveness. Properly installed electrical systems are more cost-effective in the long run. They are less likely to require repairs or replacements, and they operate more efficiently. To ensure a safe and reliable electrical installation, it is important to work with qualified and experienced professionals. Electricians and engineers have the knowledge and skills necessary to design and install electrical systems that meet all applicable requirements. They can also provide guidance on the selection of appropriate materials and equipment. By following best practices and working with qualified professionals, one can ensure that their electrical installations are safe, compliant, and reliable. Underground electrical installations offer several advantages over overhead installations. Firstly, aesthetics. Underground installations are less visible than overhead installations, which can improve the appearance of neighborhoods and commercial areas. Secondly, reliability. Underground installations are less susceptible to weather-related damage, such as wind, ice, and lightning. This can improve the reliability of the electrical system. Thirdly, safety. Underground installations are less likely to be damaged by vehicles or other objects. This can reduce the risk of electrical hazards. Fourthly, space savings. Underground installations do not require poles or other above-ground structures, which can save space. While underground electrical installations offer many advantages, they also present some challenges. Firstly, cost. Underground installations are typically more expensive than overhead installations. This is due to the cost of excavation, trenching, and backfilling. Secondly, maintenance. Underground installations can be more difficult to access for maintenance and repairs. This can increase the cost of maintenance. Thirdly, locating faults. Locating faults in underground cables can be more difficult than locating faults in overhead wires. This can increase the time required to repair faults. Fourthly, environmental impact. Underground installations can have a greater environmental impact than overhead installations. This is due to the disturbance of soil and vegetation during excavation. Despite these challenges, underground electrical installations are becoming increasingly common. As technology advances and costs decrease, underground installations are becoming a more attractive option for many applications.